Hello, in this video we are going to be discussing about the collision theory of chemical reactions as well as how that theory affects or how that theory is related to the factors affecting the rates of chemical reactions. But first we have to remind ourselves of what a chemical reaction is, and I will be using an illustration here where you have two reactants here. This is a compound composed of an atom A and an atom B, and another compound composed of the atom C and atom D. And in a chemical reaction, again, we say that it has to undergo three things. Number one, the reactants bonds must break. Okay, so the reactants bonds must break. After that, they need to be rearranged into new configurations. So instead of A bonded with B, now A will be paired with C, and then B now will be paired with D. And then more importantly, the third act is they must form new bonds between that new pairing. So now you have a reaction where it took you from the compound AB, and then you added the compound CD, and then it gave you the new substances AC and BD, right? So again, all through that process, we had to break the bonds of the reactants. A and B must break apart. C and D must break apart. And then they must rearrange. So A is now paired with C. B is now paired with D. And then the third step, they have to create new bonds. And that bond would bind together A and C and B and D. So in this case, you now have a complete chemical reaction that took you from the reactants A, B, and CD, and you produce the products AC and BD, right? So that's the idea of a chemical reaction. So what is the theory or what model can we think about when we have to analyze a chemical reaction? Well, there is one such theory, and that theory is called the collision theory. Okay, so the collision theory looks like this, right? So we propose that the reactants actually have to collide with each other. Okay, and when they collide, they could create effective collisions or they could create ineffective collisions, right? So an effective collision is such that when they collide, for example, here the Cl reacts with this molecule here, because the Cl and the Cl here collides, it actually allows the Cl to break from the N bond and create a new bond with that second Cl. And therefore here you can see simultaneously the breaking of the bond between Cl and N, as well as the forming of new bonds between Cl and Cl. So now you have that effective collisions. Because of that collision, you created a new product. Sometimes a collision could be ineffective. So for example here Cl and O collide, but Cl has no affinity, at least in this case, to bond with oxygen, or maybe the attractiveness of Cl to the oxygen is weaker compared to the oxygen's attractiveness to nitrogen. So, think of it as like a human interaction where Cl likes O, but O likes N better than Cl. So O will not let go of N, will just ignore Cl, and therefore you have an ineffective collision. So what can we take from this concept or from this process, from this assumption? Well, that there are special configurations, there are special arrangements in the collision that allows for recreation of new products, and sometimes other collisions do not allow for that, right? So to illustrate this further, let me go back to my illustration here, and let's go back to our reactants, which is A, B, and C, D. And usually if these are ionic pairs, for example, like NaCl or something like that, the A is a positively charged ion and the B is negatively charged ion. This is positive, this is negative. And this is why A, which is positive, can now pair with, sorry, so in this case, this is negative here and this is positive. Because remember, it's a positive ion paired up with a negative ion that bonds, right? So in this case, this is the reason why A now pairs with C, because A is also positive and C is negative. And now B, which is negative, pairs with D, because that will still give you a positive negative pair. So what we are trying to say here is if these two collide, right? And let's say they collide in this way. This goes towards the top, this goes towards the bottom, and they collide like that. So now B and C are colliding, but B is negative and C is negative. So they have no affinity to stick to each other. So what will most likely happen is that when they collide, they will just bounce off and nothing happens. There's no chemical reaction, right? In the same manner, if this would to collide with A and B in this manner, like that, so now A collides with D, but A is positive and D is also positive. So A and D has no affinity to, again, stick to each other. The same thing as B and C, they are both negative, has no affinity to stick to each other. So both of those cases are what we call ineffective collisions because there's no incentive for them to stick to the atom that they are colliding with, right? However, if they collide in this manner, right? This one goes that way, that one goes this way. Guess what happens? 1, 2, 3, bang. Now when they collide, A and C, A is positive, C is negative. So they have the tendency to stick to each other. And B and D, B is negative, D is positive. So they also have an affinity to stick to each other. So guess what? It could be that what would happen is this. Bang, and then they go on separate ways. So in this case, now from AB and the compound CD, now you create a compound AC and BD, right? So again, the concept of the collision theory is that these reactants, because they are in a container, they are mixed together, of course. Otherwise, how would they react? They move because, again, particles are kinetic in nature. You know, they move around. Even solids and even liquids, they move around in the container. And then when they move around, they collide with the other reactants. And again, there could be different configurations when they collide. When they collide, such that the configuration is it's not conducive to bonding with the reactant, with the atoms of the other reactant. Again, for example, like this, when they collide like that, B and C collide together, but B is negative, C is negative, also negative, so they actually would repel. There's no incentive for them to stick together. So there's not gonna be any chemical reaction. Or if they collide like this, so AB is here and CD is this one. Again, A and C are both positive. I mean, A and C are positive and negative, and B and D are positive and negative. So there's an incentive here to stick to whom they collide and break the original bond that they had. So that's the collision theory in a nutshell. So therefore, you can think of it as there are collisions that are effective, there are collisions that are ineffective, and what dictates if it's effective or if it's ineffective? Two things. Number one is the orientation, right? Because depending on which atom they collide, they could have an affinity to stick to it or not, and it could result to breaking the bond of the original substance and forming new, or no. The second factor is energy, because even if they collide in the correct way, and correct way meaning the correct configuration, A A is positive, B is negative, C is negative, D is positive. So A and C has affinity to stick to each other, B and D has the affinity to stick to each other. But let's say the collision is weak, right? If the collision is weak, so 1, 2, 3, bang. If the collision is weak, that collision would not have enough energy to break the original bonds, meaning the bond between A and B and C and D. Because remember, originally A is connected to B and C is connected to D. So if the collision is weak, it will not be enough to break the bonds of A and B, and therefore not enough to switch the bonds to A, C, B, D. Right? Sometimes also the collision is too energetic, meaning they just bounce off and don't have time for A and C to interact. Because you see, you think of it as an interaction also. So if we slow this down, it would be like this. Bang. Oh, A, you know what? I am negatively charged and you are positively charged. Why don't we stick to each other and leave these two behind? So there's an interaction between A and C. If the, again, I'm personifying these again to create a narrative in my head, right? So that it's easier to understand. But the idea is if the collision is too energetic, there might not have time, there may not be time for A and C to interact and form new bonds. There might not be time for B and D to interact and form new bonds because the collision is just too fast. So they will just bounce off. If the collision is too slow, A and C might want to interact, but the collision might not be energetic enough to break the bonds between A and B and C and D. Because remember, for A and C to bond together, it must first break its bond with B. A must break its bond with B, and C must break its bond with D. So there are two things. Number one, it must be a correct orientation, right? Because if it's like this, it's not gonna work. If it's like this, it's not gonna work. If it's this like that, it's not gonna work because A and D are both positive, B and C are both negative. Obviously, I'm just having an example here of positive, ionic pairs, but this could also apply to covalent bonds. Like again, here, it's possible that C and L, the bond between C and O, I mean, not C and L, but Cl and O, is weaker compared to the bond between O and N, such that O would say, you know what, I'm more stable with N than if I bond with you. So no, I'm just going to say no, and I'm just going to stick with N. But here, the incentive is probably that when Cl bonds with another Cl, it's actually more stable than when it bonds with N. So Cl here, the second Cl will say, okay, deal. I will let go with my bond with N so that I can bond with you. Right? So again, this example where I'm using ionic pairs, this is just a way to make it easier, but you can apply it in terms of covalent bonds also by looking at electronegativity and other stuff, right? So in this case, again, just to recap, there are two things that are important here. Number one is the orientation of the collision, and the number two is the energy. Orientation in terms of it must be the correct arrangement when they collide to allow for the atom from the first compound to bond with the atom of the second compound, or the atom from the or the second atom of the first compound to bond with the second atom of the second compound, or the first atom of the second compound. It must be the correct orientation. And number two is the energy. It must not be too little. Otherwise, it will not be able to break its bond with the original reactants and form new bonds with the products. Or it must not be too energetic, because if it's too energetic, the chances are they will just bounce off each other without having the time to interact and create new bonds. Right? So orientation and energy. And you have to remember this because this is quite important later on when we move to higher concepts. Now, please take note that uh, using here again double displacement, but you can also think of it as single displacement, right? So, for example, A B, right? And when they collide, bang! It now A is now alone, and C and B are now bonded together. So it's the same thing because orientation also still matters, because if C collides with A and A has no affinity to pair with C, so it's not going to work. So C must hit B for them to leave behind A, displace A, and C and B will be bonded together, right? And you can also apply things like maybe this is a positive ion, this is a negative ion, this is a positive ion, so therefore it needs to hit the negative ion, or because if it hits the positive ion, they will just going to bounce back. So orientation is still key there. And the same thing, energy is also key, because if it's not too energetic, it might not be able to break the bond of A and B, and therefore allow B and C to bond. If it's too energetic, it's possible that they will just bounce off, and there's no time to form a new bond between B and C, right? So that's the idea there. That's the collision theory. Now, um, aside from that nuances of the collision theory, we have to relate this to what we've learned with chemical equations, which is number one, or chemical reactions, which is number one. Again, there must be the breaking of bonds. So let me just write this one. Step one, break the bonds between atoms of reactants. Right? So the bonds of the reactants must break. Number two, there must be reorganization. Reorganize into new proportions. Proportions or arrangements. Right? So the atoms must be rearranged in a new way. And then number three, you must form new bonds. And in this case, this happens in products. But again, as I have told you, this is kind of like also, again, a little bit of a simplification, because we numbered this 1, 2, 3 as if there's a specific order for this. But in reality, this three kind of happens at the same time, because, for example, if you have, again, A and AB, which is the reactant, and C is the reactant in a single displacement, and then this hits B, right? And then it displaces. As you notice, these three things happen at the same time, right? Because as C hits B, it would trigger A and B to break, right? So that's number one. And it would reorganize the atoms into new proportion, because now instead of A paired with B and C is alone, now A would be alone and B and C would be paired up. That's new organization or new arrangement. And then at the same time, you form new bonds, because as this A and B break the bond, and as the atoms are rearranged, guess what? B and C would form new bonds. So these three things are not really kind of a it's not a sequence, but rather something that happens simultaneously, right? But again, if you want to organize thoughts in your head, it's better to say, okay, the reactants must break first its bonds and then rearrange and then form new bonds, because it's easier to understand. But deep inside, you have to internalize that these things might happen simultaneously. But again, it's there's still a benefit to remember them in a sequential manner, even if in reality they really happen at the same time, right? So if you think about this, the first part, when you break bonds between the atoms, guess what? Every time you break something, it requires energy, right? It requires energy because, you know, this A and B has a certain bond between them. For C to be able to break the bond between A and B, it requires an energy. And again, that's why the second requirement is energy. It must have the right energy to break the bonds between A and B, right? Too slow collision, it might not break A and B. Too fast, when when C hits B, if it's too fast, it might just ricochet off and not form the bond between A and B. So therefore, there must be the right amount of energy. And this amount of energy is also the same for the formation of new bonds. So think of it as breaking the bonds of A and B requires energy. Forming the bonds of B and C also requires energy. Okay? And therefore there's a threshold of the energy for the chemical reactions to proceed. So this is now the next point. The next point is this concept of activation energy, right? So activation energy is the energy required for the reactants to proceed and form the products. So in this case, for example, hydrogen gas, let me zoom this in. Hydrogen gas and chlorine gas are the reactants. They can form the products, but only if you supply an activation energy to it. And why do we require an activation energy? Because again, that energy is used to, number one, break the bonds of the reactants. Break the bond between H and H. Break the bond between Cl and Cl. And number two, to form the new bonds. To form the bond between H and Cl and the bond between H and the other Cl. Right? So it requires an activation energy. And if you notice, the activation energy is quite high compared to the energy of the products and the energy of the reactants. So in this case, this is the energy of the reactants. You supply it with an activation energy, it reacts, and then the energy goes down and form the products. Now, the best way I could kind of assert that this is true is this idea that, for example, I have here paper, right? This is paper. And as you know, paper is a hydrocarbon or primarily made up of hydrocarbon. And hydrocarbon reacts with oxygen in the air via the reaction combustion. And in fact, if I can write it here, that piece of paper, which is essentially a hydrocarbon, would react with oxygen. And as you all know, when we discuss about the types of chemical reaction, it produces carbon dioxide and water, right? So my question is, okay, I have paper here on my hand. I have oxygen there. Why isn't the paper burning? Right? So again, I have paper in my hands. Paper is supposed to react with oxygen and form carbon dioxide and water, but it's not doing anything, right? So question, what do I need to do for this paper to burn? Right? By experience, you know, I have to light a match and probably heat this up. Or get a magnifying glass, concentrate the rays of the sun to heat up a portion that would ignite. Okay? So what did I just do there? When I light the match and supply heat to this, I'm supplying energy. And whenever I have supplied enough energy, that's only when paper and the oxygen in the air react to form carbon dioxide and water. So therefore, this is how you conceptualize this activation energy. That reactants need to have kind of like an initial energy to push them to react and form the products. Okay? So in the case of paper and water, you need to supply heat to it for them to start reacting and form carbon dioxide and water. In this case, for the hydrogen gas and chlorine gas to react and form HCl, you need an activation energy. Right? Now, but sir, how come I see certain chemical reactions, like I have chemical 1, I have chemical 2, I mix them together and then they react? Doesn't that mean they don't need an activation energy? No, all chemical reactions need an activation energy. Sometimes the activation energy is small, that even by mixing two liquids, the energy of those two reactants, as they move and jiggle around because they're in a liquid, the kinetic energy they have is already enough for them to comply with activation energy. Okay? So every time you see things like an acid and a base, mix them and then they react to form salt and water, and you did not have to supply energy to it, that means that the innate kinetic energy of the jiggling of the particles in those two liquids, the acid and the base, the energy they have is already enough for them to comply with activation energy. Paper and oxygen in the air is another story. Paper and oxygen in the air needs higher activation energy to proceed. So even if I wave this paper around so that it can hit the oxygens in the air, the two do not have enough energy to beat, to comply with the activation energy requirement. Right? So that's the idea for the activation energy requirement. The second concept is, if you look at this graph, this is a graph of energy and the progress of reaction. So again, you have a level of reactants, level of the energy of reactants, and then you have to overcome the activation energy, and then once you reach that threshold, it proceeds and goes to the products. Okay, but this is just an example of an energy of an energy graph of a chemical reaction. You can have also this, right? So these are two energy graphs. Let me zoom this in. And if you notice here, these two graphs are kind of different because here, so in these two graphs, the similarities is you still have an activation energy, right? So you still have to comply this activation energy for the reactants to proceed and form the products. In this case, you have to comply with this activation energy for the reactants to proceed and go and form the products, right? But the difference is, if you look at the energy of the reactants here, the energy of the reactants is higher compared to the energy of the products here. Here, the energy of the reactants is lower compared to the energy of the products. So what can you conclude? Obviously, it's summarized here. Products in this graph have less energy than the bonds, or the bonds in the products have less energy than the bonds in the reactants. In this here, the products have more energy. It's at a higher level than the energy of the reactants. So think about this. If the reactants have more energy than the products, what does that mean? So let's take, for example, this one, right? Let's say the energy of the bonds in the paper and oxygen, again, let's just put in a number here for easy analysis, is 110 kilojoules, right? So the reactants have energy of 110 kilojoules. Then the products, when you look at this reactant, when you look at its energy, the energy is now 80 kilojoules. Obviously, I'm just making this number up, but I just want to show you, just want to show you something tangible so that you can focus on what I'm trying to illustrate. So the energy of the reactants is higher than the energy of the products. So what should immediately come into your mind? You should say, wait a minute, some amount of energy is missing. In fact, the missing energy here should be 30 joules. Because remember, 80 plus 30 is 110. So therefore, if the energy of the products, of the reactants rather, is 110 kilojoules, and the energy of the product is just 80 kilojoules, it means you've lost 30 joules. You have lost 30 joules. Now, what do you mean by you have lost 30 joules? It means that energy escaped from the system, right? And when energy escapes from the system, more often than not, that energy is translated to heat energy. Okay? So when you burn paper, for example, and again, these examples are just arbitrary. When you burn paper, let's say the energy of the paper bonds and the oxygen bonds is 110 kilojoules. Then when they react, they form carbon dioxide and water, and it's now just 80 kilojoules worth of energy in the bonds that in them. It means you have lost 30 joules, right? But again, in science, nothing is ever lost. Energy is always conserved. Energy cannot be created nor destroyed. So guess what? These 30 joules became heat. If the reactants have more energy than the products, that means the reactants, when it forms the product, it has to let go of some of that energy. That's why the energy is less, but that energy is usually released from the reaction to the environment. And whenever heat is released, guess what? What would you feel? You would feel an increase in temperature. Okay? And this increase in temperature is exactly what happens in the paper, burning a paper in the chemical reaction when you burn paper. When you burn paper, heat is produced. And again, this is now related to one of the evidence of chemical change, change in temperature. Because when you burn paper, heat is released. And when heat is released, you as an observer absorbs that heat. And therefore, you detect an increase in temperature. So for this reason, because heat is released, heat is flowing outside, flowing from the chemical reaction towards outside, we call this chemical reaction exothermic. Exo means to exit, thermic means the heat. So heat exits out of the chemical reaction, and when it exits out of the chemical reaction, you as an observer would feel that heat, and therefore you would feel that the chemical reaction produces heat. That's an exothermic chemical reaction. So again, take note that all of what I've discussed just stems from our analysis of this one, because think about it, if the reactants have more energy than the products, then guess what? Some of the energy must have been released. Otherwise, why would this have less energy than the reactants? So it must have released some of the energy, and that energy released usually is in the form of heat. And again, if you want a number illustration, 110, now it becomes 80 because the products have less energy. Guess what? 30 joules must have, not joules, but kilojoules. 30 kilojoules must have been released. And that heat released would be felt as a rise in temperature, and therefore we call this an exothermic reaction. So all reactions that produce heat or raises the temperature are exothermic. Now, looking at the second graph, it's opposite. The reactants have less energy than the products. Okay, so again, just to illustrate that, if the reactants have less energy than the products, like let's say again, just for illustration purposes, let's put some numbers here. let's say 150 kilojoules in the reactant side, and then in the product side, it's now 200 kilojoules, right? So reactant side, product side. So what does that mean? Well, how come the products have more energy than the reactants? And again, you cannot create energy out of nothing. So guess what? It means that somehow, instead of releasing energy, it must have absorbed 50 kilojoules, right? Because 150 plus 50 is 200 kilojoules. So now this is the opposite, because the reaction does not release energy. It actually absorbs energy from the environment. Okay? So what that means is, if I am the observer and this reaction happens, energy actually flows from me towards the reaction. So the chemical reaction absorbs some of the energy. And when energy flows away from me, I detect that as a temperature plunge. I detect that as the temperature is moving or falling, because again, temperature is related to heat. It's just a measure of how energetic particles are. So if the energy is absorbed, then this becomes less energetic, temperature plummets, and therefore in this case we call this an endothermic reaction. So endo means inside, to flow towards, rather than exit out of. It's to flow toward the chemical reaction. So thermic, so heat flows towards the chemical reaction rather than is being released. So in these endothermic reactions, these chemical reaction would feel cold. Okay, so if you have chemical A and chemical B, I mix them, they react. If it's an endothermic reaction, guess what? After they mix and they react, it feels cold to the touch, because rather than releasing energy, it absorbed all the energy from the environment. Okay, so all in all, the conservation of energy is not violated. The reason why the reactants here has more energy than the products is because energy is given off. See? But in this case, the products have more energy than the reactants because energy is absorbed. And when energy is given off, heat is given off, that reaction feels hot, like burning paper. But when the chemical reaction is endothermic, it's the opposite. It absorbs energy and it feels cold to the touch, right? So you have chemical reactions like things like are used in military applications, like instant ice packs. So you have two liquids actually, and there's a barrier inside, and you have to break the barrier so that those two liquids will mix. And when those two liquids will mix, they chose liquids that when it reacts, it forms an endothermic reaction, and therefore it absorbs the heat from the environment. So that instant ice pack becomes colder, so you can now apply it for whatever applications that you would like it to have. So that's endothermic reactions and exothermic reactions, right? Now, how does this relate to the collision theory? It's the same thing, right? So the particles still collide. It's just that the bonds of the reactants has more energy than the bonds of the products in an exothermic reaction. But in an endothermic reaction, it's the opposite. The bonds in the reactants have less energy than the bonds in the products. And again, in the real world experience, that translates to whether the chemical reaction feels hot from the perspective of the observer or feels cold. If it's exothermic, it feels hot because it releases more energy. That's why the energy here decreases. But for endothermic, it feels cold because it absorbs the energy. That's why the energy of the products all of a sudden goes higher. But take note, even if the reactants here is higher energy, has higher energy than the products, and here reactants has lower energy than the products, the activation energy is still higher than both of them. right? The activation energy is still higher than both of them. So you still have to require this activation energy to proceed, right? So you still have to require this activation energy for them to proceed, right? So that's the idea there. So the next discussion is aside from activation energy, is this idea that the chemical reaction has a certain rate. Okay, so rate of chemical reactions. So the rate of chemical reaction is, as the name suggests, the rate is simply how fast a chemical reaction proceeds. So, for example, if you have burning a piece of paper, you burn a piece of paper in minutes, it goes away. The whole thing becomes ash, becomes carbon dioxide, and some carbon, depending on what hydrocarbon you are burning. And that's a fast chemical reaction. But if you have a piece of iron nail, and that iron nail reacts with oxygen in the air and it rusts. That rusting process takes time, right? So it's not like you take out an iron nail and then 1 second you look away, when you look back, it's now rusted. It takes hours and hours. So the rate of a chemical reaction depends on a lot of factors, right? Some chemical reactions are just inherently fast. Some chemical reactions are also slow. So what are the factors then of the rate of chemical reaction? So now we take a look at factors affecting the rate of chemical reactions. And again, rate of chemical reactions is just how fast a chemical reaction proceeds. So number one is just the nature of the reactants. Okay? The nature of the reactant. So if you remember your periodic table, if you look at the elements of the periodic table, again, you have these things called the noble gases. And these noble gases are very stable. Things like helium, neon, argon, those things are stable. They don't need other elements to react with to be stable. They are stable by themselves. So that means naturally, if you pick those elements like neon will never react with other, not never, but will rarely react with other things because it's stable in itself. So, and what's the reason for that? It's just simply its nature, because of how its electrons are distributed in its valence shell. So there are just certain elements that are more reactive than others. Like for example, sodium. Sodium is very reactive than, let's say, iron, right? If you put iron in water, it will probably rust in a few hours or a few days. But if you put sodium in water, the whole thing explodes because sodium is just a more reactive atom than iron. So that's the first thing, nature of the reactants. It's just built into what atoms are there in the reactants. Are the atoms more electronegative? Are the atoms are the atoms can the atoms be in ionic form or not? Can they form covalent bonds or metallic bonds? It depends on the nature of the reactants. So simply put, some atoms and some chemical reactants based off of those atoms are just more reactive than other stuff, than other atoms and other reactants. The second one is the temperature. Okay, so the temperature this concept goes back to our discussion about the gas laws. Remember when we discussed about the gas laws, temperature is just how fast, or it's the average, or it's related to the average kinetic energy of the particles. So guess what? If the particles are less energetic, they will move slower in the container, right? Or this would move slower in the container. If they have higher temperature, guess what? They move fast around the container, right? So why would temperature affect the rate of chemical reactions? Again, it has to do with the collision. Because if the temperature is slow, therefore, again, we use this single displacement reaction. If the temperature is low, they're moving slowly. When they collide, the energy might not be enough to break this bond and form new bonds, right? So it depends on the temperature. So the higher the temperature, the more likely are they going to react, right? Because if the temperature is higher, obviously it's more energetic, and more energetic means it might break the bond between A and B and form new bonds, right? So that's the reason why temperature factors in to that to factors in to how fast the rate of chemical reaction is. Number three is this idea of surface area. The surface area of the chemical of the reactants involved. Surface area, or we sometimes we call this particle size. Okay, and why is that? Well, the idea is this. Let's say you have, and for simplicity's sake, let's just take a combination reaction. So chemical A reacting with chemical B, for example. If chemical A is in chunks, right? In chunks, like this. So this is chemical A, chemical A, chemical A, chemical A, and it's in a cubic form. It's in a granule, and then this is also chemical B, and chemical B is also in a granule, right? So let me just complete this. When they collide, the most number of them that could collide is 4, because this side could collide with that side would collide this, that side collide this side, right? It's 4. So they are the only, or maybe let's change that. Let's take a look at which atoms here are exposed for collision. This one, 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 this one. So you see, all of the outer atoms are open for collision. The inner atoms, you cannot collide with them because they are inside, right? Obviously, this is two-dimensional drawing. Obviously, it would be better if you have a three-dimensional configuration. But the idea is the center atoms cannot collide. And remember, collision is, again, the main theory. You have to collide with the other reactants to form. For B, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 are available for collision, but the 4 are locked in. They are not available for collision, right? So kind of like saying, or maybe maybe we can create a three-dimensional version of this, if you give me some patience, some time. So let's say all of these cubes are chemical, are reactants, right? If the particle size is large, right? If the particle size is large, like this, right? And again, give me time to set this up. And let's just make a cube. Let's just make a cube. Like so, right? And then one more layer. So you see, that center particle, it's not available for collision because it's locked inside, right? So it's locked inside. So guess what? When this chunk of when this chunk of reactant moves around in the medium and hits with other reactants, there are some atoms that are hidden inside, which are not available for collision. So if the particle size is large, the surface area exposed is small because some atoms are locked inside. But if I'm going to pulverize this particle, now all of a sudden, all of those reactants are available for collision. And if they're available for collision, meaning they could have more collisions. More collisions means more successful collisions. More successful collisions means more products formed. And therefore, the faster the chemical reaction is. Right? So, one example of this is if you can have firewood. If you have firewood, a big chunk of firewood, like, right? So if you have this big firewood, guess what? The wood exposed are just at the surface, right? But the wood that are inside the firewood, the molecules that are inside the firewood, are not exposed for collision. So when you burn this firewood with fire, right, allowing it to react with oxygen, guess what? The molecules that are inside, locked away, are not available for collision. So you have a bigger particle size, right? Bigger particle size, but the surface area exposed. The surface area exposed is smaller because it's only this and that and that and this and that, but all the molecules inside are not exposed for collision, right? Therefore, you have less collisions, less collisions, less effective collisions, less effective collisions, less products produced, slower rate of reaction. But think of this. What if you pulverize this wood, right? You pulverize this wood. And one way of doing that is probably uh, using a wooden saw, and then the shape, the wood, the smaller wood byproducts of that process, the sawdust, right? The sawdust. If you take sawdust, one chunk of sawdust, it's not now one chunk of wood. So now the particle size are smaller because instead of one block of wood, you now have one chunk of sawdust, and each sawdust is obviously separate from the other sawdust particles. Right? Guess what? If you like throw it up and it scatters, and then you light a lighter, guess what? It might actually explode. Why? Because in that sawdust configuration, all of the molecules that are locked inside the wood were actually released because it's now in smaller pieces. So smaller particle size, but surface area is big because a lot of the molecules are exposed to the oxygen. And therefore, when you do that, you scatter sawdust like that, and then you light fire, it might actually explode. And there are certain demonstrations of that. Maybe the most common one that I saw in YouTube is cornstarch. So you have cornstarch, and then you have a candle, and then you blow cornstarch through that candle flame, and it actually makes a bigger fireball because cornstarch are in smaller particles. And again, if you have smaller particles, there are the reactants are not locked inside the chunk, right? And therefore there's a bigger surface area, and therefore more particles to collide with oxygen, meaning more particles to collide with oxygen, more collisions, more effective collisions, more products produced, faster rate of chemical reaction. So that's the idea for the surface area. Now the next part is what we call the presence of a catalyst, or in that case, an inhibitor. Catalyst and inhibitor are opposite ones. Catalyst makes the reaction faster. An inhibitor makes the reaction slower. So if A reacts with B, if you add an inhibitor, its rate of reaction will be slower. If A and B reacts and you add a catalyst, its reaction would be faster. So think of the rusting of iron. If you have a rusting of iron, if you have iron, if you coat it with oil, the oil would probably act like an inhibitor. It would prevent the iron from reacting with the oxygen slower. It would prevent it from happening, so that the rusting process slows down. So oil in that sense is an inhibitor, kind of. And a catalyst would be something like salt. So salt water would actually make iron rust faster. So I know that because my house is just across the sea, and all of the metal structures in the house, including my our piano, is actually rusted. I mean, the strings of the piano are actually broken and cut because it accumulates rust from the sea salt water. So in that case, salt is a catalyst for that reaction, right? So the first thing that you need to understand is that there are these things called catalysts and inhibitors. Catalyst is a chemical that makes a chemical reaction faster, the rate of chemical reaction, and an inhibitor makes it slower. But the question is, why would a catalyst make it faster, and why would an inhibitor make it slower? So the idea is now the activation energy, right? So I can show you here an illustration of the activation energy and what it does when there is a catalyst, right? So here, this is the energy level of a reactant, and then this is the energy level of the products, and then you have the activation energy, right? This is the level of activation energy. Now this green one is the reaction when it is uncatalyzed. There's no catalyst. This purple or violet one is a catalyzed reaction. So if you notice, the activation energy of the catalyzed reaction is at a lower level than when it's uncatalyzed. So therefore, what does a catalyst do? It lowers the activation energy, lowers the energy requirement. Okay, lowers the energy requirement. And if you lower the energy requirement, then you don't need a lot of energy. And if you don't need a lot of energy, a lot of those reactions would become effective. An analogy would be like an entrance examination, right? So you want to get into a university, and let's say the university requires that you get 90% of all the test questions. And if you get 90%, you would you would pass, and you would be able to enroll in that university. So that's the energy, that's the requirement, 90%. Now what if the university, so now when students take the entrance examination, some students pass, some students fail. So in this analogy, we say that the students who pass would be the effective collisions, the collisions that create products, and those students that fail will be the ineffective collisions, those collisions that did not produce products. Now, say for example, the university decides, you know what, 90% is too high of a requirement. Let's just say, let's lower it to 75%. So any student who can get 75% would pass our entrance examination. Question, what would be the effect of that? Obviously, it's a no-brainer. When you lower the requirement, many students will pass. So if you lower the requirement for the number of items that you must get correct, many students can now enter the university because you've lowered the requirement. The same thing here. If you lower the activation energy, a lot of the collisions will quote-unquote pass the requirement and produce the products, right? So I hope you get the analogy. So an inhibitor, therefore, is the opposite. An inhibitor increases the activation energy. It makes the requirement even higher. So it's tantamount to saying, okay, let's increase the grade requirement from 90 to 98. You cannot be enrolled in our university if your entrance score is not 98%. What would be the effect? The effect of that would be less students would pass and less students would be able to enroll. So in the analogy of our chemical reactions, less collisions will be effective and less products would be produced. So therefore, an inhibitor increases the activation energy, making it more difficult to produce the products. Because remember, the activation energy is this barrier from the reactants to form products. A catalyst, on the other hand, lowers the activation energy. So when it lowers the activation energy, it's more likely to pass that requirement and more likely to form the products. Okay? So I hope you now understand the concept of a catalyst and an inhibitor. So, but now you might be asking, but sir, okay, I understand it. Catalyst lowers the energy requirement. Inhibitor increases the energy requirement, and therefore that translates to, slower rates of reaction or faster rates of reaction because of the effect of either there will be more effective collisions or less effective collisions. But how does that work in the real sense? How does that work in terms of the products, for example? Well, it's like this. Let's say you have chemical. So again, these are just arbitrary, but this is off the top of my head. Let's just say you have chemical AB reacts with chemical C, and then it forms AC, and then B is isolated, right? And it has an energy requirement. Let's say the energy requirement here is, again, let's just put a number so that, again, it's easy to digest in your head. Let's say 100 kilojoules for this reaction to proceed. But what if A and B can react with another element called D to form AD plus B, and then AB AD plus B can react with C to form AC plus B plus D. So this is the first chemical reaction. So the first chemical reaction is AB plus C. You need 100 kilojoules of activation energy for it to proceed and form AC plus B. So again, single displacement. But what if you have this, where AB doesn't react with C, reacts with D to form AD plus B, and then later on, that AD plus B reacts with C to form AC plus B and D, right? So instead of going directly, it's like another route. But this is the idea. But what if this here requires only 40 kilojoules of activation energy, and this requires 40 kilojoules of activation energy, right? So guess what? If you summarize, the reactants here are A, B. So if you summarize, A, AD here is in the product side. AD here is in the product side, but AD here is also on the reactant side. So let's cancel that out. B here is in the reactant, but also on the product side. So cancel that out. And then D here is in the product side. D here is the product side. So guess what? It's still the same reaction. So now when you cancel out these things, A and B plus C, A and B plus C is still equal to AC plus B, AC plus B. right? It's still the same reaction. It took 2 steps, but it's still the same reaction. So you see, this is a direct reaction. A plus AB plus C is equal to AC plus D. In this case, you took 2 steps, but the effect is still AB plus C is equals to AC plus D. But guess what? This reaction took 100 kilojoules. But these two reactions took only 80 kilojoules. So therefore, if you let A and D react with C to form AC plus D, you need 100 kilojoules of activation energy. But if you have this two-step process, guess what? It only takes you 80 kilojoules, because the first step only takes 40 kilojoules, and the second step only takes 40 kilojoules. So therefore, you save on the energy, right? So you save on the energy. So now when you rewrite this equation, you would say A plus B plus C is equal to AC plus B, right? But guess what? You don't want this because it takes more energy. You want this part. But what did you do in order to enable this? You use D. So now you put D here. Okay? So because think of it as D is temporarily used form, but actually it also cancels out in the reactant side. So now this class is now a catalyst. So if you remember our chemical formula, whenever you write a chemical above this arrow, this is a catalyst. So that means that A and AB plus C will react only if D is added. Right? So guess what? When this is the reaction, compared to this without the D here, without the catalyst D, takes 100 kilojoules. But this with the D takes 40 joules in the first, 40 joules in the kilojoules in the first step, 40 kilojoules in the second step. So overall 80 joules, 80 kilojoules. So guess what? This chemical reaction is faster than that chemical reaction, right? And as a result, and this takes less energy than that, and as a result, this becomes faster. Okay? So I hope you understand that, why the catalyst is like that. It could also be that if we used E here, A plus B plus E, and then it becomes here AE plus B, and then AD, AE plus B, and then E, and again, still the same concept. It could be that this takes 60 joules, and this takes 60 joules. So now, if you take the direct route, it takes 100 kilojoules. But if you take this 2 steps using E, so it's not now D, using E, guess what? You will use 120 kilojoules. You would use more energy instead of less. So guess what? If this takes less energy, this needs more and less energy than this, then this is a lower activation energy than that. So guess what? This is faster than this. So therefore, when you use this chemical equation, this is now not a catalyst, it's an inhibitor. E is an inhibitor to that reaction because it makes the reaction slower. Okay? Another example that I could give you is, again, this is a loose example, but just to, in case that you did not understand that, say for example, you have a flight from Manila directly to New York, right? And then this cost, again, I'm just eyeballing this, 1,200 USD. But then you have another trip, and that another option. That option is Manila, stop over to, let's say, Japan, and then Japan to New York. But Manila to Japan only costs, I don't know, 100 USD. And then Japan to New York costs 900 USD. Again, just an example. If you notice now, if you took the connecting flight, Manila to Japan and Japan to New York, you would spend $1,000 only. compared to when you take the direct route. So in this case, again, in the analogy, this is the original chemical equation. It takes more energy, but if you have a rerouting kind of mechanism using another chemical, but still end up with the same product, in the end, you will end up using less energy, and therefore this is faster. Now, obviously, that's the weakness of the analogy. In the analogy, this is not faster because you will have to take 2 flights. But in the chemical reaction, what matters is the energy usage. So you use more energy here, which is the analogy for the money spent. You use less energy here, so this one would become faster than this route. But again, it could be opposite. It could be that if you take this route here, this becomes 500 USD and this becomes 1,500 USD. So now this direct route is 1,200, but this connecting flight configuration gives you ask you $2,000. So that case is like the inhibitor case where you actually spend more energy for that, right? That's the second example. The third example that I could show you is it could be that the catalyst or inhibitor would do something like this. So for example, this reacts with this, right? And the mechanism is it must collide at a specific angle like this. When it collides here, it reacts and forms 2 products, right? But the problem is because this has to collide at a certain specific orientation. If it's oriented like this, it will not hit it. If it's oriented like this, it will hit the S, but it will not react. If it's oriented like this, it will hit the A, but it will not react. And the reason for that is because this has a lot of freedom. It can rotate, and in fact, in 3-dimensional space, it could rotate in different orientation, and therefore hitting the right orientation is difficult, right? Now, sometimes a catalyst could be an enzyme, and that enzyme sometimes does this. It might, so this is an enzyme, which is another molecule, right? So I'm just drawing it here. So what happens is that enzyme could attach. So this is an enzyme, which is actually just a catalyst, but in biological system. So when you have a catalyst, but in biological system, we call that an enzyme. If that enzyme binds with this, guess what? This molecule cannot rotate. So if it cannot rotate, and moreover, only the R is exposed. See, the S and the A are hidden in the enzyme because it's sticking to the enzyme. Only the R is exposed. And so if only the R is exposed, guess what? When this reactant comes over, it's now easier, take note, it's now easier to hit the R. Again, let me explain the thesis. The thesis is, if this is not bind to an enzyme, this could rotate in 3-dimensional space. And if it can rotate, then that means when it hits, it doesn't necessarily hit the R. It could hit the A, it could hit the S, it could hit other stuff. But if it binds in an enzyme like that, its movement is limited. Now A is not exposed, S is not exposed, only R is exposed, and moreover, because the enzyme is big, this cannot rotate and this cannot move freely in space. So therefore, this reactant can easily, it makes it easier to hit the R and form the new product. So a catalyst could do that. So again, there are many ways to imagine what a catalyst does, why it makes the chemical reaction faster. Obviously, it could be the opposite. You could have a structure where it actually hides the R. And if it hides the R, guess what? Now this reaction, this reactant would now find it very difficult to react with the R. So in this case, this is an inhibitor, not a catalyst, because it makes it difficult for the collision to happen. Right? So that's the idea there. That's the idea. There are, again, many ways to imagine how a catalyst or inhibitor affects the rate of reaction. But again, you need imagination to kind of visualize them. And again, when you have imagination, when you have a narrative, a story in your head to kind of fall back into when things get difficult, believe me, it becomes easier to understand why uh, presence of catalyst or like that makes it more difficult or easier for the chemical reaction to happen. The last factor affecting chemical reaction is the rate of chemical reactions is the concentration of the reactants, right? So this one is pretty much very self-explanatory because, for example, if you have a container, right? And let's just take a combination reaction. So let's have atom C and atom O combining to form CO, for example. And again, they have to traverse this container and they have to collide effectively and form CO. If there's only one atom and one atom of there, then it would take a while for them to find each other and hit each other, right? But if there are now more COs, more C's and more O's, right? Guess what? When they move around the container, they have more chances to collide. More chances to collide means more effective collisions. More effective collisions, more products. More products means faster rate of reaction. So if you have this, you would say that the concentration is low because in this container, there are only one atom of C and one atom of O. That's a less concentration compared to when you have two atoms of O in that container and two atoms of C. Much more if you have 100 atoms of C and 100 atoms of O, then the likeliness of them to collide would be higher. You know, kind of like if you're trying to find a wife and you're a scientist living in a science experiment bunker in Antarctica, and you only meet, I don't know, 5 other persons there in the lab. So there's less chance to interact with the opposite sex. So therefore, you are less likely to find a wife. But if you are in the outside world, you are in America or any other place which has a lot of population, right? So there are many girls out there, many boys. You can meet more and you can interact and collide with them, and you know, produce products or create bonds, right? So again, a loose analogy, but you get the idea. So in summary, there are 5 factors affecting the rate of chemical reaction. Number 1 is just the nature of the reactants themselves, because some reactants are just more reactive than the others, and again, that lends to the idea of what atoms are in that compound, because some atoms are reactive, like some atoms are noble gases and they are not very reactive to those things. And then the second one is the temperature. Again, the higher the temperature, the faster the rate of reaction, because that means more energy to overcome the activation energy. And then you have the surface area of the reactants or the particle size. And take note that this is a little bit confusing because particle size and surface area are opposite. Bigger particle size means less surface area, and smaller particle size means more surface area exposed, right? And then after that, we have the presence of a catalyst. That is what is said in the book, but for me, I'll just going to generalize it and say presence of a catalyst or an inhibitor. A catalyst makes it faster, the rate of reaction. An inhibitor makes it slower. And again, how would it make it faster and slower? Again, there are many ways to imagine that. Just go back to the video to try to understand some of those mechanisms. And then lastly, you have the concentration of the reactants. So just to summarize, nature reactants, it depends on the reactant. Some are just reactive, so makes the chemical reaction faster. Some are just very non-reactive, makes it slower. For the temperature, the higher the temperature, usually the higher the rate of reaction. Surface area or particle size, the bigger the surface area, that means the smaller the particle size, that means the faster the rate of reaction. Okay? And then the smaller the surface area, that means the bigger the particle size, that means the slower the rate of reaction. For the presence of a catalyst will make the chemical reaction faster. An inhibitor makes the chemical reaction slower. Why? The catalyst makes the energy requirements lower. The inhibitor makes the energy requirement higher. And again, there are many ways to imagine how the catalyst and inhibitor does that. For the concentration, the higher the concentration, the faster the rate of reaction. The lower the concentration, the lower the rate of reaction. Okay? So again, that's how the collision theory, again, this theory that the reactants must collide with each other with the proper orientation and the proper energy for them to break the bonds of the original reactants, reform into new configurations, and form new bonds for the new products, right? That's how related the collision theory is to the activation energy and ultimately to the rates of reaction, namely to the factors affecting the rate of reaction, namely the nature of the reactants, the temperature, the surface area or particle size, the presence of a catalyst or inhibitor, and the concentration of the reactants.